Okay, thanks for the introduction. My name is Chungwook Sim. I'm an associate professor at University of Nebraska-Lincoln, and this is our team members deployed from ACI 133 Disaster Reconnaissance Committee. I will present our mainly focused on the proportions of the reinforced concrete buildings that we have observed in Turkey. I may have a slight overlap, but I do want to touch that we were base camped here in Gaziantep. We were visiting these different cities that Remy mentioned, and he was mentioning about the peak ground velocity demand exceeding the maximum considered earthquake. These are the cities that we visited, and these dots are the buildings that we surveyed as a team of members of 40 members. So these are the cities that we visited. We visited quite a lot. The city Antakya that had the most severe damage you saw from Remy's presentation here is about 3.5 hours from Gaziantep, so we spent 2 days there when we were down there. So these are the cities, the 10 cities, and after the 1999 earthquake in Turkey, they installed a lot of ground motion stations along the fault line. So these triangles are all the ground motion stations installed right next to the fault, where we can receive and retrieve information of peak ground acceleration, peak ground velocity. And this circle here is where the first earthquake epicenter of a moment magnitude of 7.8 happened. And these are the cities that we visited. This was from the second earthquake, which was about 9.5 hours apart, with a moment magnitude of 7.5. So both earthquakes were huge, and it can be considered as, some claim that as a twin earthquake. Before I start my presentation, I do want to show a short drone footage of the building stock and the development in some of these cities. You'll see a lot of buildings. I want to show, and so that all of you can have a feel of what type of construction you can see in these cities. So Nurdagi was the first city that we visited from our base camp. A lot of 5 to 7 story buildings here. This is Turkoglu. Along the street, you'll see about, again, 5 to 7 story buildings, some entirely collapsed, some remaining with severe damage, either with structural or non-structural damage. This is another area where I'll talk about tunnel form construction. The question was asked in the previous presentation. You'll see some buildings in this complex that had totally collapsed. And Antakya was in the southern part of Turkey, and you see a lot of damage here. The city is vacant. It's empty, so there's no one living in here. Either because there's a lot of structural damage, or even with buildings that have less structural damage, you see all the non-structural damage that you see in the city. The city has been evacuated, and some buildings are scheduled for demolition. So you see that, again, 5 to 7 story buildings here. In the same city, Antakya, there are higher buildings, and the buildings that we surveyed while we were there were around 2 to 16 stories. So you'll see higher and more recently designed and constructed buildings as well. So this is Antakya. Again, you'll see some non-structural damage on the roof. We went back to Kahramanmaraş, and we visited here several times. If you go to the west side of the city, you'll see a lot of development and newly built constructed buildings, which are compliant to the Turkish code after the 1990 earthquake. So you'll see a lot of newer constructions here. I'm not going to go through all the cities, but at least I just wanted to show you how much buildings you're looking at. We visited 10 cities, and there's lots of structures, reinforced concrete buildings. Moment frames, or either with tunnel construction, shear walls that we visited. So this is a short video of the buildings that we visited. So Remy did talk about the ACI approach. There were a lot of buildings when we were visiting these cities that were totally collapsed. Obviously, we won't be able to collect any data from these buildings, but around these buildings, there were buildings that we were getting into. We would record the coordinates, we would measure the distance between the columns, measure the dimensions of the columns, measure the dimensions of the walls, And we would take a lot of photos in and outside the building and document. And this building actually had light damage, but as you can see, all the non-structural masonry infills, unreinforced masonry infills, coming out of plane. So there's no one living in this building right now. So what we do with these data, why are we measuring the wall dimensions and the column dimensions? Those of you who are familiar with the ACI 133 data reconnaissance efforts may already know the wall index and column index, and maybe heard about the Hassan index as well. Basically what we're measuring here, we're trying to get all the wall dimensions at the base, at the first level. The unreinforced masonry wall, we only consider 1/10 of the stiffness of the unreinforced masonry wall, and we divide it by the total floor area multiplied by the number of stories, which would be the mass, the entire mass of the building, versus the stiffness at the base. So that's what the wall index and the column index is. How was the wall index and the column index of the 242 buildings that we surveyed? So this is a plot where the black dots are representing severe damage. The white dots are other damage, either light or moderate damage. And you see a lot of buildings don't have much wall or don't have much column and have a lot of damage here. So I will continue my talk and try to show you some observations on the field regarding the proportions. These are two buildings that were right next to each other. One had severe damage, one didn't. This may be a repeat, but at the column base, as Remy mentioned, the details were not great. You would see longitudinal bars and the columns which are not confined at the base well, and sometimes the prevent bars, or I don't know if it was buckled by the vent, but you would see a lot of buckling of the longitudinal bars at the base, the column base. We were walking around the building, and because the unreinforced masonry infills are all are gone, you can actually see through, and we saw this shear wall in here. We walked in, and you would see, measured the distance. The spacings are not great, but not bad. But not necessarily the best, because the longitudinal bars were not really tied together with the transverse reinforcement. Here, you would see buckling of a couple of these longitudinal bars, eventually fracturing the bars. So this shear wall is gone. This is this building, and from the Hassan plot that the wall index versus column index plot that I showed you is a building here where you have the minimum of 0.3% wall and 0.1% column index. So that's where this building is. The building right next to it, and it's at the same dot, but it's behind this black dot where there wasn't much damage going on with this building. And this happens in an earthquake reconnaissance effort. You would see the building that has the same design, the same construction, while one building right next to it would fail and one would not. But there are some slight differences here that the shear wall here, in east-west direction is slightly offset, giving more eccentricity between the center of mass and center of rigidity, I guess. But that may not be the reason that it failed, but that's one of the two buildings that we surveyed earlier. And you see again, from the same building, there wasn't much damage with the structural frame, but you would see masonry infill damage. In Antakya, we were surveying this building here, and this is a building here with the wall index and column. So it has about slightly more walls, this building. We started from this side of the building to the survey, realized that it's not a rectangular building, which is difficult to make measurements. But we spent a lot of time here. You see a lot of shear walls. These shaded areas on the drawing are the shear walls, and you'll see the others of the columns. The shear wall was heavily damaged, but this is the building where I also have the same details that Remy was showing from the earlier presentation. Some bars are, the longitudinal bars and the beams are terminating in here where the crack initiates. Some actually initiates at the joint too, and we wonder what's going on. The bars are not connected through the joint, and if you see the bars. There's a slight a 3D LiDAR image taken from my phone, and you see the bars fractured here, and this bar here. I mean, it's not even in the joint. Yeah. So per details that you would see. Again, from the same building, you would see details where the bars, the longitudinal bars and the beams are not really confined, and there's no spacing between these bars. So they're just slitting back and forth during the event and eventually buckling the bars in the beam. Well, also in Antakya, there were buildings that this was probably an example of a tunnel form. So 16-story buildings, lots of walls in both east, west, and north-south direction. So this is the building here. But we still have severe damage in this building. In the first floor, we go down, and this was one of the fewer buildings that the transverse reinforcement, it doesn't really look like a reinforcement here, poor transverse reinforcement, and you see basically the core is gone. You see a lot of bars buckled, so this shear wall is gone. It has a lot of walls, but with the poor detailing, it didn't work well. What about buildings that actually had good details? So there were 3 buildings here, and I think Santiago will talk about this building as well. The details were not bad compared to the other buildings that you saw here earlier. Wall index, the minimum is around 0.04%. Say this estimated drift, because I think Remy and both Santiago made some measurements from the buildings that are still standing from the first floor, and the estimated drift was about 6%. 6%. So you go in here and you see better details, but the building's still overturned with a huge drift, and that's what I want to highlight here. So we were looking into these buildings. It went through a tremendous cycling, and you see all the damage and overturning. Let me skip this one. But you see this wall basically shifted. It's similar to the building that Remy was showing, and all the bars buckled here. So a lot of movement, a lot of drift was happening in this area. What about some of the buildings that may had more walls and maybe not sure about the details? This time, not to make the mistake, we were walking around this building, and it has a weird configuration, as you can see. It's a building that I would not try to document, but because it would take hours to make all the measurements. But we went in, and I don't know if you can see from the back, this shear wall basically have one hairline crack here. No damage. This building was clean, and we wondered what's going on. And there's some cracks in the beams, but basically there wasn't much damage. So with this triangular-shaped building, we start making measurements. There's not many shear walls, but this is about the same as the amount of shear walls that you saw from the first building. But now, because of the triangular floor area, the wall index and the column index is here, about doubled of 0.6%. And it actually survived. Now, also, these triangular buildings may have, torsional concerns, but they have a shear wall located here. So center of mass, center of rigidity may be close to each other. So this was a building that actually survived the event with a 0.12% minimum wall index. Around Karamaras West area, there were all these tunnel form buildings. These are our ACI, some of our team members, Santiago, looking at the splices, counting the number of, some students were counting the number of bars fractured. But some of the other team members remaining went inside the building to document the building. And I wasn't sure if I want to spend much time in this building where the 2 buildings collapsed. So I just went down and checked the shear wall, and the shear wall wasn't, it was heavily damaged. But we were fortunate to actually receive a drawing about this tunnel form building. As someone asked before, there's lots of walls. But in this case, and some of the other buildings were remaining still, you see that it's only in one direction. East, west, there's not many walls, and these are all openings on this side. So this is the building in the wall index versus column index plot. You have lots of walls, which is definitely good, but you have walls only in one direction in this case. These are buildings that they call Toki buildings. built and designed by the government for low-income population. And actually, these buildings did very well. We heard about it. We went there. I was fortunate to be able to enter to one of the units, and this is the measurements that we made. Lots of walls in both directions. The walls are laid out in a symmetric way, and you see 0.74%, 0.57% wall index here. And this is the building up here. So you put a lot of walls, and it survived the building. Actually, one story, we went all the way up to one of the units that allowed us to get in, and they actually offered Turkish coffee after we made all the measurements. The gentleman actually took photos and posted on social media. I didn't know that, but anyway. So later on, we also received drawings, and the numbers that we calculate from the drawings are similar to this wall index. So I want to make a summary here. We had a large team of about 40 people. We have full information about 240 buildings. 2 to 16 stories are the buildings that we surveyed from 10 cities over the 11 days, so lots of work. You've seen examples where large drift demands and elements with inadequate detailing lead to structural failures. All of you know that. This is well known, and that's why we're making efforts to improve the detailing of our structures. However, some of the buildings with better details did have lots of non-structural damage with the large drift here. And you saw that building that had better details that overturned as well. Not only from Turkey, but from several past efforts, we see that there is a clear correlation between the structural performance under earthquake demands and the number of walls and the number of columns at the base, which contributes to the stiffness. So buildings with smaller and fewer walls, as you saw from my presentation, that are more likely to have structural and or non-structural damage. How do we survive? Well, I think controlling drift by increasing the stiffness, meaning by putting a lot of walls. And from our plot, and Santiago is going to talk about some other earthquakes as well, if you have more than 0.2% wall of your total floor, in both directions, you saw that the case when you don't have it in both directions, it could be problematic, will highly improve the structural performance regardless of the reinforcement details and the quality of construction. So that's something that's important I want to highlight, that if you put a lot of walls, the building will perform much better, regardless of the details and construction quality. Okay. I do want to, there's one more slide. So thanks to ACI for funding this effort. It was a team effort of many people from the industry and academia. Not only we worked hard in the field, but when we returned back, we would always do discussions after every day. So, following up.
Any questions for Chungwook while he's here? Again, we can come back at the end.
Thank you, sir. My question is to know: how important is it to ensure that the cover of rebars is going to be solid, that it doesn't spoil, that it stays there? Is it something that matters, or it doesn't matter at all?
I don't think it matters in such a drift so large. It's gone quickly, just like the unreinforced masonry infills that would just be gone right after the event starts. So it's more of the confinement and the reinforcement inside.
Regarding the confinement, is that important that the concrete in the core of the column could disintegrate in blocks? Is that important? And can that be prevented by using, for instance, fiber reinforcing?
I've seen examples in other presentations where fiber reinforced concrete actually does help some of the performance in the joints. But what I wanted to focus here was not really about details, because sometimes you don't really have much control of the details. Although we know that improved details will make better performance of the buildings. So here what I wanted to more focus was how much dimensions of the walls and the columns you have as a cross-sectional area versus the total floor area.
Thank you.
Simple solution.
Were you able to get any information on the grade of the bars that were this big?
We actually, that's a good question. We actually had, from one of those beams, we saw a bar. They used some of the reinforcing bars, the same bars that are used in the beams, to use it as a chair, as a spacer. So one bar was actually dropped on the floor, and one of the colleagues, Dr. Zomez, he brought the bar back to the lab and actually tested it, and it performs exactly the same as what you would typically expect from a ASTM A615 conventional bar.
Yeah, I've seen one of your picture. It shows that it seems that the torsional mode becomes the first mode. Does it also affect?
One of the buildings?
I don't know. One of your slide shows that the position of the shear wall. I think it will result the first mode as the torsional
so
mode.
I mentioned about it, but I mean, definitely irregularity and torsional irregularity will contribute to some of the behavior of the buildings. But here, again, the focus was how much wall and how much column you have. So, and again, even if they are located at the same location with less eccentricity, some buildings would fail, some buildings will still be standing. So I'm not sure if that's the sole reason that you see a lot of shear damage in the shear walls.
Just a short question. You had mentioned early on when you were listing the 240 or so buildings that got full data, that the completely collapsed buildings you were not able to get data from. But then in one example, it seemed like you mentioned that one building that did topple, you were able to get drawings. So in the end, how many of the 240 buildings actually included completely toppled buildings, or was it solely the ones that you measured that were standing either with severe or non-severe structural damage?
Yeah, that was the build. We have buildings about, I think, 20 or 30 buildings, drawings of 20 or 30 buildings, yep. And others are all just based on our measurements out at the field. That 6% was an estimate from Santiago and Remy, who were out at the field just measuring from the first floor drift. So it's just an estimate.